All right, I'm going to get started. Today, I'll talk about a variety of topics to do with probability, randomness, and independence, um, and how this relates to choosing samples specifically, and a few other things. There'll be at least one thing in here that may be of interest to those that are doing legal studies or pre-law. So I'll get started if I can press buttons. Also, we are recording, so be aware of that. If you have questions, you can put them in the chat or raise your hand and I'll unmute you. Otherwise, please stay muted. If you want to wait until the end, I will turn off recording and I can answer questions with recording off at the end. So what exactly are we doing here? We're trying to get from our sample to a good picture about the world. So we're thinking about if we go out and we pick 100 people and do a survey experiment, or we go out and we pick 100 people and we investigate the way they vote, or what party they're registered with. And we start trying to draw inferences. How do we apply that 100 people or whatever the number is to a larger sample? And this is something we have to do with scientific research. It's also something that you have to do if you get involved with polling. Although it's not exactly the same, but a lot of the probability work and the distributions and things work in similar ways. They're based on the same math. Excuse me. And one of the big things that we have to do in the scientific half of this is one of the things is to eliminate the idea that that something is happening just due to random chance. One of the other things that we have to do is eliminate the possibility that things are due to confounding variables, to other variables that affect things. So if we have a variable, if we're looking at the relationship between voting and income, well, there are lots of things that can affect voting other than income. There are probably some things that may affect both income and voting. There may be some things that income affects that then affect voting. And there may be things that don't affect voting directly, but they do affect income, and so they have an indirect effect. So there are lots of different relationships, and there probably are even more relationships than just the three I described. So there are lots of things that can be going on. And actually, for if we start talking about survey experiments and other kinds of experiments, well, randomness actually ends up working for us there because it helps us to take those out of the picture. So what am I talking about with randomness and probabilities and things? So we should start with some definitions. First of all, an experiment is something where we control the conditions and we apply a treatment. So it's something where we are able to make certain that all the other variables are held constant, usually by assigning people randomly to two different groups. And one of those groups gets a treatment and the other does not get the treatment. And in clinical trials in medicine, this is really obvious. The treatment is the treatment. It's the drug, it's the therapy, it's whatever's being tested. We use the same language of treatment in survey experiments or other experiments in political science. But the treatment in a survey experiment is going to be that we show them an article, or in the paper we looked at, the paper we looked at the other day, they get shown two different graphs. So the control group in the article, in the one article, the control group didn't get shown any graph. One group got shown a graph that was exaggerated but consistent with the text. And the other group got a graph that was not exaggerated, but wasn't consistent, but downplayed things compared to what the text did. So, and that was all by random assignment. And the random assignment meant that we could worry, maybe not completely not worry about outside variables, but we could worry a lot less about things like differences in income, race, party registration, those kind of things, because we could assume that randomness was going to give us a roughly equal mix in each group. We can do some other things if we're dealing with small groups to take care of some of those other variables too, or to test them anyway, like asking what party you're registered with. But that's an experiment. It's also called a random controlled trial. It's controlled because we control everything except the treatment. And we have a control group that doesn't receive it. And it's random because we randomly assign to the groups. What's an outcome? And so an outcome has lots of meanings. So outcome is the result of the experiment, but outcome also factors into probabilities, because we talk about in probability, we talk about a favorable outcome, and favorable doesn't necessarily mean what it does in everyday conversation. So favorable outcome just means the outcome we're predicting or the outcome we're expecting. Heads and tails, if we say heads, we assign heads as the favorable outcome. It doesn't mean heads is better than tails. It just means we've assigned it that. And probability is the number of expected favorable outcomes divided by the total number of outcomes. So if we are flipping a coin, there are two possible outcomes, heads and tails. We set favorable as heads, favorable as one possibility out of two total possibilities. The probability is 0.5. It's half. But those are outcomes. Heads and tails are our two possible outcomes. That's also called our sample space. Heads or tails. Voted, didn't vote. Went to war, didn't go to war. Those are binary. They don't have to be binary. The sample space could be the numbers 1 through 10. The sample space could be, and the sample space, when we get to things like classifying countries as democracies or not, if we use the liberal democracy index from VDEM, it's 0 through 1. It's every possible number. It's a continuous thing. So with continuous variables, it's the probabilities at any single point. Literally, the probability at any single point, because it's a single point, is or approaches 0. But so we have to do different things with those continuous. They're not quite as simple. But we'll start by thinking about discrete variables. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 as whole numbers. If it's a uniform equal distribution, the probability of 5, that's one result out of 10. So 1 out of 10. The probability that the number will be between 5 and 7, well, that means 5, 6, 7. If it's between 5 and 7, inclusive, 5, 6, 7, that's 3 possibilities divided by the total, which is 10. Yes, was there a question? You can unmute yourself and ask. Sorry, I saw a hand go up, but I didn't catch who it was. Okay. All right. If I see it again, I'll call on you again. Um, so and an event would be this specific set of outcomes. So in the case I just gave, the event would be 5 through 7, or the event would be 5. It's that group of outcomes that we care about. It's the group of outcomes that we're looking for. So a little bit more about probability. First of all, probability runs from 0 to 1. You can also say 0 to 100, because, and you do that just by moving the decimal place 2 points. But typically we talk about it 0 to 1. We say it's on a unit scale. 0 to 1 is the unit scale. 0 is impossible. It just cannot happen. Um, so something that cannot happen. And then 1 means it's an absolute certainty. Everything falls in between. And the probabilities of the possible events has to add up to 1. So if we go with heads and tails, there's a 0.5 probability of heads, a 0.5 probability of tails. 0.5 plus 0.5 equals 1. That always has to be the case. It can't exceed 1. There's no such thing as a higher than certain probability. It just can't happen. There's nothing better than a guaranteed probability. There's nothing worse than an impossibility in terms of probability. It's always between 0 and 1. So if you're doing some work and you come up with a probability that's negative, that's not possible. It means there was a mistake somewhere. If you come up with a probability above 1, unless they've converted it to a percentage scale, but above 1 or above 100% does not exist. It means somebody's made a mistake. So realize that. And it's always got to add up to 1. If the probabilities don't add up to 1, either somebody's made a mistake or they may have just left something out. So if the probabilities are equal probabilities of the numbers 1 through 10, so number 1 has a 0.1, number 2 has a 0.1, number 3 has a 0.1, we add all those up, they add up to 1.0. They leave 5 and 6 out and just don't report on them, well, then you're only going to have 0.8. If you only come up with 0.8, you need to be looking, saying what's going on, and then you look and you say, oh, well, they didn't tell me the probabilities for 5 and 6. But they should add up to 1. Almost everything's going to fall in between, because the things that are impossible and the things that are guaranteed just almost don't exist in the real world. I mean, there are things out there, but impossible in terms of politics, we're almost always dealing in the realm of the possible. Is it possible that in a free and fair election, a candidate would get a 100% vote or a 0% vote? It's almost unthinkable that either of those would happen. Somebody is going to not like the guy. And even if the person is the most hideous candidate imaginable, somebody is either not going to know what's going on or they're going to hate the other guy more. So the 0 and 100, those are the kind of cases that they're not going to happen. So finding things that are impossible or guaranteed, I guess maybe I could say that the 0 and 100 are impossible. But it's very rare that we're going to find things that are either impossible or guaranteed in political science. So one of the things that's important to understand is this law of large numbers. If we flip a coin one time, the expected probability, the expected value of flipping one time is, well, there really isn't one, because it's a perfect probability of heads and tails. So we can't just talk about expected probability, but we can talk about expected probability of getting heads on a single coin flip. And it's exactly 0.5. It's 0.5. If we do it 10 times, the expected probability is that we'll get 5 heads, 5 tails. Is that likely? Not really. It's almost more likely that something else is going to happen. It's that we would get exactly 5 heads on 10 flips is we know that it is the expected probability. It is the most likely thing to happen. But we also know, if you've ever done it, that getting 6 or 7 heads is not unusual. You can even flip 10 coins and get a run of 10 heads. It happens. It's as the number gets bigger, the more unlikely it's going to be that you're going to get that run extending. So a run of 100 heads is approaching impossible to happen. It's still possible, but it becomes much less likely. And as we get that bigger and bigger number of trials, that bigger and bigger number of draws or flips, the more it's going to converge on what the expected probability is. So with 100, the expected probability is 50 heads, and we're going to see in reality, if we actually do this, that the number gets closer to the 50% mark on coin flips, the more coin flips we do. This is not terribly surprising. This is not terribly surprising, and it's mathematically provable. And there's a reason we call it the law of large numbers. We don't call a lot of things laws. We tend to talk about theorems and things, but this one's a law, the law of large numbers, and there's a reason. It is something that just intuitively, theoretically, and in the real world works out to be true. This is one of the reasons that we always want, all else being equal, a bigger sample size. Our ideal thing, if cost were not an issue, would be we have the entire population. We make one of them, half of them the control group, randomly drawn. The other half of the entire population is our treatment group and gets the treatment. Of course, cost doesn't allow for that. And we don't actually have to get samples that big for it to actually work. Another important concept to consider is the idea of independence and dependence. So independence just means that when one thing happens, statistically, mathematically, it does not change your opinion about the second thing. So if I draw out of a hat and then roll dice, the draw from the hat doesn't affect my beliefs about what the die roll is going to be. If I roll dice tomorrow, it doesn't change. It doesn't change my odds of whether I'm going to get a particular number on the roll compared to today. The day of the week doesn't make a difference on my dice roll. If I flip a coin at noon or flip it at midnight, it doesn't affect my rational statistical belief about whether it's going to be heads or tails. Now, it may affect your belief if you have some kind of superstition, but mathematically and empirically, it doesn't affect our beliefs. In set notation or in probability notation, this is the probability of A, if we know B, is just the probability of A. It's the same. Knowing B does not change it. So the probability of A conditional on B is just the same as the overall probability of A. Dependency, on the other hand, is when knowing something about B tells us something about A. Knowing something about the value of the Dow Jones Industrial Average at closing time on Friday tells me something about, since the stock market's closed today, it tells me something about what the Dow Jones Industrial Average is going to open at tomorrow. It doesn't tell me exactly, because it can open up or down. And lots of really bad things could happen, or lots of really good things could happen that could make the jump or drop really big. But still, what happened at the close on Friday gives me a baseline, and the further we move from that baseline, the less likely it is. That may be an overly complicated example, because there are so many other variables involved. Knowing a student's SAT score tells us something meaningful about whether they're going to succeed in college. Is it 100%? No. But statistically, it gives us a baseline as to their likelihood of success in college. It does affect, and it's not just superstition. It's a meaningful effect. So our assumption about any two variables in the real world is that they're independent. But if they're not, that tells us something's going on. And so we start to talk about causation in that case. It's not that there's a definite causation, but there's something that warrants investigating. And if two things are independent, that is one thing that we can say, though. If they're absolutely independent, if we can establish statistically that two things are independent, we know there's not causation going on. And that's one of the things that we really try to do when we talk about falsifying a hypothesis, is we create a hypothesis, we run statistical tests to determine, are these two things dependent or independent? And if it turns out they're independent, the hypothesis is rejected. And that's what we're really going for when we start talking about hypothesis testing. So another thing, so something to remember when doing sampling is that replacement matters. So what this means here is, if we're talking about draws from a hat and we want to know about probabilities, if we draw 4 numbers from a hat for everybody in the room to determine which row they're going to sit in, and the first person puts the number back, then it's a 25% chance for the second person. But if the first person doesn't put the number back, then the second person is only going to be drawing from the 3 remaining rows. So they're going to have, instead of having a 1/4 chance of all 4 rows, they're going to have a 0 chance of the row that's been removed and a 1 in 3 chance of each of the others. So replacement and not replacement matter. They affect the probabilities. So in sampling, we typically want to do with replacement and retain those identical probabilities. So there are situations where you can't do that. One person is, if what we're drawing for is who's going to be the discussion leader for the day, if we were going to do that, if we had enough class periods for everybody to do that one time, and we drew, well, we would have to take that person out. We would have to, because otherwise other people aren't going to get the opportunity. So there are situations where we're going to do without replacement. But typically, if we want unbiased results in our sample, we're going to try to do with replacement in a lot of cases. If we're talking about, though, dividing into control and treatment groups, once you're in the control group, you stay there. But replacement and not replacement also tell us something about probabilities. So what about determining the probabilities of more than one event? So I talked about the hat draw and the coin flip, or the hat draw and the dice roll. Those are pretty simple because they don't affect each other. But there are a couple of different ways we can look at this. One is, what if the events are mutually exclusive? So that is things that can't happen at the same time. Things that can't happen at the same time would be if you have a choice between candidate X and candidate Y. You can pick one or the other. If your probability of picking candidate X is 0.25, we're going to know what your probability of picking candidate Y is because they have to sum to 1, or they have to have a difference. They have to sum to 1. You can't do both of them. So the probability of doing both is 0. If they're not mutually exclusive, then they can overlap. So like you can have a feminist bank secretary. I just drew that from a famous statistics example that I can't remember the whole thing of. Actually, a famous behavioral economics example. But you can have a feminist secretary. The feminist and the secretary are two totally different things. They can happen together, or they cannot. They're not mutually exclusive. So we have two different rules for how to handle these things. One is the addition rule, and this is the probability notation. And I'm going to show you an example of each of these two. I'm going to read you the notation. I'm going to tell you how it reads. The probability of A union B, that is the probability of both happening, equals the probability of A plus the probability of B minus the probability of A intersection B. I'm sorry, I told you that wrong. A union B is the probability of one or the other happening. Probability of A intersection B is the probability of both happening. So probability of A union B equals the probability of A plus the probability of B minus the probability of A intersection B. I'm going to give I'm going to give a simple example that should work to 0. The probability of A union B, if A is heads and B is tails, equals the probability of A heads, 50%, plus the probability of B tails, 50%, minus the probability of both, which is 0. So the probability of A or B, heads or tails, is 1. Because the probability you can have heads and tails in a single flip is 0. So the probability you're going to flip heads plus the probability you'll flip tails is 0.5 plus 0.5 minus 0. The probability that you will get heads or tails is 1. The multiplication rule is for independent events. And it is that the probability of A intersection B, that is the probability of both happening, equals the probability of A times the probability of B. That one's complicated enough. I'm not going to try to walk you through it verbally, but this is the addition rule. So if A is red and B is blue, and so the probability of turning out purple is the intersection. Purple is the intersection of red and blue. So the probability of A union B, that is the probability of both, is the probability of red plus the probability of blue minus the probability of the intersection. So why is that? We have a total of 90, right? So we take 40 plus 50 minus the intersection is going to be the probability of having red or blue and not purple. So it's the probability of A plus B minus the intersection. What about the probability of A intersection B? It's just the probability of A times the probability of B. So if our two things are high and low and left and right, then the probability of high times the probability of right is the probability of being high and right. The probability of left and low, the probability of left times the probability of low is the probability of being left and low. If we want to know the probability of left and high, we take the probability of high times the probability of left. If we want to know the probability of right, low, we take the probability of low times the probability of right. That is the rule for independent events. So if that was not complicated enough, I'm going to give you the idea of conditional probability. I am not probably going to give you a lot of this on an exam, except maybe asking you what it's called and what you use to figure it. And it's called conditional probability. And you use Bayes' rule. The probability of A given B. So the probability of A, if you know that B has occurred, is the probability of A and B divided by the probability of B. There's actually a better way to write that, but this is called conditional probability. So this is if you know somebody's education level, does that tell you about something about their probability of voting? Yes. So we can say, what's the probability of voting given that a person is college educated? That's one thing. Or we can say, what's the probability of voting given that a person has at least a high school education? That's a different thing. Age affects voting, right? We can say, what's the probability that someone's going to vote given that they're in the 18 to 25-year-old age range? What's the probability that they're going to vote if they're in the 65 or older age range? And the 65 or older is more likely to vote than the 18 to 25. It doesn't tell us whether the specific individual is going to vote, because yes, some 18 to 25-year-olds vote, some 70-year-olds don't. So it's not an absolute, but knowing the age tells us something about the probability the person will vote. Another example here, if voters identify as independent, we know that a certain percent support a policy. I saw a statistic the other day that showed support for voter ID laws among voters, not among activists or politicians, but among voters. It's something like 85% among Americans generally. It's over 90% with Republicans. It's over 85% with independents, and it's around 80% with Democrats. It's actually an overwhelming majority among all three, if you talk about voters and not activists or politicians. But knowing that someone is a Republican, I know that they are more likely to support voter ID laws. If they're an independent, they're slightly less likely, and if they're a Democrat, they're still likely to support, but slightly less likely. If they happen to be a Democrat politician, they're highly unlikely to support. If they're a Republican politician, they probably support. We start to get in the range when we start talking about politicians. Sometimes we get to the point that we're talking about guarantees and impossibilities almost, because politicians are very polarized. Whether individual voters are, maybe not as much, but politicians definitely are. So where's this come into play? Well, this is an interesting one. There's something called the prosecutor's fallacy, and it's because of using flawed logic with regard to conditional probability. And the reason is because we have distorted beliefs about the base rate. The base rate is in probability. Probability is the favorable outcome. And in this case, the favorable outcome might be guilt or innocence. So it depends what we call favorable. Whatever outcome we're looking for, divided by the total possible outcomes. So if we have a fingerprint match and we know that that's 1 in a million, then the prosecutor is going to say, well, it's 1 in a million that this guy's innocent. We got a match. It's 1 in a million. But if we're in the Houston area where there are 6 million people in the area and it's a 1 in a million chance, that means there are 6 people out there that would match that fingerprint because they don't completely match the fingerprint. It's on points of identification. So it's a 1 in a million, but of the possible people out there in Houston who might match it, if there are 6 and we have 1 guy, that actually means that there's the possibility of him being innocent is 5, because there are 5 people out there that are innocent that share that fingerprint match. 5 out of 6. Or in this example, they say 10 million people. Well, I said 10 million people, but I should have just said 6 so I could make it fit the Houston area. But 10 million people, there are going to be 10 people, and only one of them is going to be guilty, which means that actually it's a 9 out of 10 chance that the person with that fingerprint is, if we don't know anything else. If there's other evidence, oh, guess what? Then we're talking about it's a probability of A given B, but at that point it's not probability of A given B anymore because we've got other evidence. That's C, D, F, G, H. And we can update our probabilities with each additional piece of evidence, but it doesn't always work out exactly like you would think it did. You think that you're adding in a 1 in a million chance that the person is innocent when you add the fingerprint, but if it's a big enough city, you may actually be only adding a 1 in 10 chance that they're guilty, and not a 999,999 in a million chance that they're guilty. It actually flips it. And so prosecutors do this. There's a similar thing with probabilities that someone is innocent given the accuracy rates on breathalyzers. You actually have a similar thing going on with it that's more complicated that I don't want to explain. But accuracy rates don't always tell us exactly what we think, or these 1 in a million chances don't always tell us if we don't think about what the base rate is properly. So in practice, when we're trying to determine from a sample, so I'm backing up to our sampling again, we're trying to determine how accurate our sample statistics are. When we have maybe 100 people out of the whole population and we know what the mean is, or we know what the variance is, or the standard deviation, and we want to talk about the population, How do we do that? Well, the sample number is called the statistic. So the sample mean is the statistic for the sample. And we want to get to the parameter for the population. So we want to get from the sample mean to the population mean. Well, that's actually why we do the n-1 when we figure sample statistics. That's Bessel's correction. That's one of those extra credit type questions. But Bessel's correction, n-1, allows us to get from a biased sample mean to an unbiased estimate of the population mean. So some things, if we want to think about, like, how are we going to figure out if something is independent or not? If we knew that the probability of somebody being an independent voter and the probability of somebody being pro-choice is 0.5, and we knew that those were independent, which they aren't, then if we wanted to know the probability that they would be both, it would be 0.4 times 0.5, it would be 0.2. That's assuming that independent voter and pro-choice are independent. They probably aren't. What about checking if things are mutually exclusive? The probability, we just look at what's the probability of them occurring together. If it's 0, then they're mutually exclusive. All of this is about how we get at cause and effect. It's about how we get at correlation versus dependent relationships. How do we get from mere correlation to causation? How do we get from a sample to the full population? This is why we're worried about this stuff, and we combine this with probability distributions, and we combine this with random sampling in order to provide control and experimental groups. If we're able to do an experiment, we do other things if we have observational data, but it's all about trying to figure out what is mere random chance and what is actual cause and effect. I am going to stop recording, and I'm also going to stop, there we go, stop recording, and then